sometimes it's nice to know how fast an object is moving around in a circle and also how fast the central angle is moving, and those are examples of linear and angular speed. So before I get into this example with the fan and showing you those formulas, let me just remind you back to a formula that you might remember. Distance equals rate times time. And if we just, instead of rate, that means speed, that means velocity, those all are interchangeable. So I'm going to rewrite that instead of r with a t. And then our distance, when we're dealing with a circle, that would be the distance around a circle. And so I'm going to replace that with s. And then if I solve for the velocity, divide both sides by t, so I get velocity is equal to the distance around the outside of the circle, that's the s, divided by t. Okay, so right, those would cancel, so v equals s over t. And that's where this formula comes from. Velocity is equal to s, which is the length of the distance around the circle, divided by time. Okay, so then we also have a couple other formulas. This is the angular speed. That is just the change of our angle over time. So it's theta divided by t. And then a little bit of algebra will get us to this next formula right here. So, and that one's pretty useful. So let me kind of show you how to do that one. So if we have s is equal to r theta, okay, so arc length is equal to the radius times the angle, then we plug that in to our velocity. So instead of s, we're going to replace that with r theta all over t. Okay, and then, well, what's theta over t? Theta over t. Theta over t, that's w. Okay, so we can replace that with, it would be radius times theta over t, which is the angular velocity. Okay, so that's where this formula comes from. And we're going to use both of those here in these next couple of examples. Okay, so that's where this... Okay, so let's do a few examples. So we have a fan length is 3 feet and it's rotating 7 revolutions every 2 seconds. So we want to find the angular speed, just how fast is the central angle changing? How fast is that moving? Okay, so we have a length, that's a radius. Okay. And then we have 7 revolutions every 2 seconds. So 2 seconds, that's my time. 7 revolutions, that's my angle. And a full revolution would be 2 pi. And so my angle would be 7 times 2 pi, and that's in radians. Okay, find the angular speed. All right, angular speed, I'm looking right here. And my formula is angular speed is equal to theta over t, and so I have, let's see, theta, that is 7 times 2 pi radians, and my t is 2 seconds. So my angular velocity is 7 pi radians per second. And that one's done. Now let's look at one where it might be a little bit easier to relate. Okay, so a bicycle wheel is 26 inches in diameter. That is a radius. Oh, that's a diameter, so my radius is half of that. Radius is 13. The wheel rotates at a rate, that means speed, right, or velocity, of 120 revolutions. And remember, a revolution, that's 2 pi. And so we're doing 120 of those. That's my angle. And per 1 minute, okay, so t equals 1 minute. Find the speed that the bike is traveling. Okay, so we want to know the speed, usually that's in miles per hour. Okay, so let's see, we have a linear, we're talking miles, you know, the speed that the bike itself is traveling along the road, that's a linear speed. Okay, and we've got two formulas we could use for that. V equals S over T, or V equals R times angular velocity. Since we know the angle and we know the time it's taking, so it's not going to be very hard to figure out our angular velocity. So let's use this formula. All right, so angular velocity, that is given by the angle divided by the time. Okay, so here we go. Angular velocity, that would be the angle, and we have our angle of 120 rotations, so that's 2 pi's, and the time is 1 minute. Okay, now we're going to use that, and we're going to find our linear velocity. So linear velocity is the radius times the angular velocity. So the radius is 13, the angular velocity is 120 times 2 pi. I might as well just write that as 240. 240 pi over 1 minute. This is in minutes. And this was in inches. Okay, so we have 13 times 240. That is 3,120 pi. And that would be in inches per minute. So now we need to convert that to miles per hour. Let's see, I'm going to start just working on my my time first, okay? So this is 1 minute, 60 minutes. I want to get rid of minutes, so I'm going to put that in the numerator, and that's the same as 1 hour. All right, so now my units will cancel there, and I'll be at least in inches per hour, which isn't quite what I want, but I'll get there. Okay, so 60 times 3,120, that is 187,200 pi, and our units now are inches per hour. So now we need to work on our inches. All right, so let's see. I want to get rid of inches, so I'm going to put those down here, and I'll convert that to feet. So let's see, 12 inches is 1 foot, and then I don't want feet, I want miles. So I want my inches to cancel, and then I also want my feet to cancel. Okay, so I'm going to cancel those out. 1 mile is the same thing as 5,280, and if you don't know those conversions, you can just look it up. How many feet are in a mile? Okay, and so then we'll just work that out. Everything up in the numerator, we just only have 187,200, 87,200 pi, and everything canceled except miles. And then down in the denominator, I have 12 times 5,280, which gives 63,360. So let's see, in the denominator we have hours. This is the only thing that wasn't crossed off, and in the numerator we have miles. So our units are what we needed, which is miles per hour. So then if I just multiply my numerator times the pi there, and then divide by 63,360, we'll get approximately 9.3 miles per hour. And that is the speed of our bike.